All right. Well, welcome, Michael and Tim. I'll go ahead and turn the time over to you now for your presentation, and then we'll have questions as we go.
Okay, thank you for the opportunity there, John, inviting us to speak at your seminar. Just a little bit more information about us personally. Tim's my nephew. Our grandparent, my father and mother, they joined the church in Australia and then came over to New Zealand to teach at an LDS high school that was in Hamilton, New Zealand, closed a number of years ago. So we both come from that LDS background, and we've both served missions. I went to Ireland, Tim went to Washington, DC. So it's a real privilege to be able to connect with you guys at BYU and to see some of the work that you're doing. And so we're grateful for this opportunity to be able to share some of our work as well. Thank you. Next slide. Okay, this is sort of a snapshot of our research team. It's located at 3 universities in New Zealand: University of Auckland, University of Waikato, and Massey University. Consists of 11 academic staff and 3 postdocs and 16 postgraduate students at the moment. And it's a mix of chemical engineering, mechanical, and software engineers. Okay, next slide. So our research centre, known as the Ahuora Centre for Smart Energy Systems, we've been formed with government funding with the purpose to assist New Zealand to decarbonise its industry and obviously to assist the global effort to do that. Now, this is how New Zealand ranks on the OECD list of emitters per capita. And you might be a bit surprised as to how bad we are. 5th worst emitter per capita. We have about 5 million people in the country. So we're sort of like a big state of America. Washington State's probably the equivalent in population. So you might ask, what's causing us to have so many emissions? Next slide. Well, if you look closely at this busy slide, on the right-hand side, you'll notice there's a big chunk of our emissions coming from agriculture. So agriculture and food production is one of our main industries, and the animals and livestock are giving off a lot of methane. So they contribute up to 48% of our greenhouse gas emissions. So that's a real challenge for the country. If you look down some of the other areas where the carbon dioxide is the main emitting gas, on the energy side, we are about 80 to 85% renewable energy. So we've already decarbonised our electricity production quite a bit. There's still a little bit more to go, and that will happen. Transport will need to electrify. But over in the industrial heat and power, combined, we have about 17.5 megatons of CO2 equivalent that we're needing to transfer over to some other form of energy production. We also have got a lot of forestry as well that helps us. Okay, so this is a breakdown of what our industrial sector looks like. And as you can see, the food processing areas of dairy and meat is the largest sort of industry sector. We have chemicals, iron and steel, cement, petroleum refinery, aluminium, pulp and paper, and mining and quarrying. So that food processing area is an area that we've been researching in for some time, and we will be assisting New Zealand in that space and also with some of the other chemical industries.
Michael, just a quick question here, back on that slide. Is that unique? Are there other countries where food processing is the top emitter?
Well, there's, if you go to the United States, there may be some states. There may be some states in America that have a lot of food processing as well, if you sort of break it down. But from the country's point of view, Ireland obviously has a lot of cows. But I don't know if they have as much as us Our livestock numbers are fairly high. They outstrip the people by quite a bit. Okay, next slide there, Tim. Now, another driving force for change is we are part of the carbon trading scheme, and the carbon price is starting to rise, and that is affecting the economics of what the industry does. And so, this is likely to get worse as well. Next. Tim, if you want to just, yeah, okay. So, what's that going to go to? Clearly in Europe, it's rising as well. So the government has a number of schemes that they're pushing. It's quite a plan for decarbonisation with the current government. There's the Resource Management Act is going to be banning coal boilers. So there is real push for the industry to change. And the industries that we're working with, they're under a lot of pressure to look to move to biomass and to make their plants more energy efficient. There was a Climate Change Commission report that was done by a broad range of individuals to sort of outline the areas that we could attempt to address. Government is looking to turn that into a policy and to firm action. An example of some action is government is investing in decarbonising industry through a fund. It's called the Getty Fund to help incentivise change. They're looking to help to part fund projects that lead to CO2 emissions. And so there's a number of projects that we've been involved with as well. Okay, thank you. Now, one of our largest companies and dairy processing companies is one called Fonterra, and their CEO and Ku have already made the statement that they're going to be getting out of coal. That's quite significant. These are some of the largest dairy factories in the world that are looking to electrify and have biomass mixed in with their energy supply. Next. So our aim is to use process integration and digital disruption to enable the process decarbonisation of our industries with the least cost pathway. And the least cost pathway, that brings in the old adage of engineering, where we engineers do for $1 what any fool can do for $10. And this is very true when it comes to coming up with innovative ways of assisting industry to decarbonise. Next slide. So let's just talk a little bit about the focus of our research. Sort of three main areas here. We're going to be looking closely at within the process itself and what are some ways to make it more energy efficient. We'll also be looking at industrial sites, and we'll be looking at the community and the factory edge and how we integrate things with regions and the renewable energy production that's occurring in various regions around the country. The factories are located out there in rural areas in a lot of cases, and there's opportunities for renewable energy to be gathered in those regions. So looking at the process, these are some of the ways that we're looking to reduce demand, efficiency improvement, integration of new technology, heat pumps, for example, mechanical vapor recompression, say in evaporator systems. We'll be looking at improved energy conversion. If we are going to be using electricity, how do we get the multiplier effect of heat pumps? How do we make sure that our boilers are as efficient as possible with recuperators in there and to lower the exhaust temperatures? And then, as I said, as we go out to the factories and in the communities, if we're going to have solar panels on the roofs of houses and various factories, and we're going to have wind turbines, how do we use the factories as, in a sense, energy storage mechanisms that enable those renewable energy to be used most efficiently. As you can see, New Zealand is long and slender. There is a backbone electricity grid that runs through the country, and where the factories are at the edge of the grid, there's real value in trying to integrate the renewable energy where it is being used. Next slide. So this leads on to what we're doing in the digital twin space. Those of you that have been studying digital twins already know that's a digital representation of something that looks like a real process, behaves like, and connects to a physical system with the goal of improving decision making and, in our case, efficiency and reduced emissions in the way the plant is run. Now, what you see in front of you is also is borrowed from some of the work of your guys. We've just added the retrofit option there. We've been doing work in the retrofit space and how we can add heat exchangers and heat pumps in a smart way. But we're looking at all of those scales. We've got process control experts in our midst, those that are very good at online optimization and process design as well. Okay, so if we have a look at digital twins, going into a little bit more detail there, let's have a look at what looks like, behave like, and connects to, breaks down into. So when we talk about looks like, there's a number of ways in which we can do that. We've got a one-dimensional model, typical process flow diagrams. You've got a 2D model, which might be a piping instrument diagram, all the way to a 3D CAD model. So there's various levels of complexity that we can go to there. Over on the behavior, behaves like, those of you that have been involved in process simulation know that it all starts with steady state mass balance. We can then go to more sophisticated multi-discrete states, pseudo-dynamic sort of analysis, and then ultimately in a full-scale dynamic modeling. And over on the connects to, once again, there's a number of states that we can exist in where you can use your digital model to guide what's happening in the factory, but mainly through a human, indirectly influencing what happens in the factory. But, imagine we've got the digital twin up and running. It's able to connect one way and assist the factory with directly communicating and guiding some of the optimization. We've called that a digital shadow. And then ultimately a two-way direct communication system is what we're calling a digital manager. So all three of those we're considering in the class of a digital twin, with really that top right-hand corner as an ambitious goal to work towards. Thank you. Now, here's another way of sort of expressing the looks like fidelity versus the behaves like fidelity, with a bit of a breakdown of various ways of modeling, from simple block diagrams all the way to full transient CFD modeling with intensive computational requirements to make all that possible. So, where are we operating at the moment? Well, we're developing sort of steady state process simulation with some physical layout considerations. So it's in that middle section that we think there's room to develop a lot more in, and to be able to apply those tools to industry to assist them in decarbonising. Next slide. So when it comes to how you apply digital twins, within a life cycle assessment, so a number of stages. We've got the design phase, we've got the operational phase, and we've got the service phase. There's quite a list of ways that these digital twin could be applied. The goal here is to be accurate enough that industry is able to use the information that is being gendered from the digital twin to assist them in de-risking projects. Whenever we put up ideas that enable them to decarbonize, there's concerns about, how risky is this? If we can do pretty reliable what-if analysis, that assists in helping to de-risk them. So there's a level of prediction that's got to be done. We've got to obviously come up with optimal solutions that are low cost, and that will potentially lead to lower carbon industries. And so that's sort of further expanded there in those three areas of design, operation, and service providing. And this is an asset optimization sort of cycles that we see things going through, both on the operational side and on the asset improvement side. With the digital twin, we want to be able to have access to plant data. We need to be able to reconcile that. We are hoping to develop machine learning methods, be able to have a dynamic digital shadow that can then be used for adaptive control sort of at the operational level. And then on the retrofit and the changing of the assets, where you can use it sort of as in digital model form, look at automated retrofit analysis, use it in the digital shadow, and then provide advice to the plant to make changes. So that's just a quick introductory summary of some of the work or some of the areas that we're working in and moving forward and on the digital twin side. I'm now going to ask Tim to sort of step in and show you a couple of case studies of sort of PhD work and postgraduate study work that we are doing from some of the students. Okay, hand it over to you, Tim.
Thank you, Michael. So we're going to talk about two pieces of work that have happened fairly recently, I guess you could say. The first is going to center around this idea of how do we deal with plant measurements and how do we create some machine learning models from those measurements. And the second one is going to be around low carbon design, decarbonization through better design and electrification. So this piece of work was primarily driven by our PhD student who's at the University of Auckland, Isaac, and it's also being presented at a conference that's down here at Australasia called Advances in Digitalization of the Process Industries. So his work focused on this real dilemma, and when you go to digitalization, of what we call unexciting industrial data, or sometimes it can also be called unbalanced data. Now, this concept is a little bit tricky to, I guess, understand in the first instance, but essentially what we've got is, this is some data that's from one of our geothermal power stations that we work closely with. And it's the idea that we run the plant at a particular state and we try to control it to that state or nearby that state. And as the air conditions and everything changes, it might just go off to slightly different states, or maybe the steam flow and the amount of geothermal fluid coming out of the ground slightly changes instead of in terms of flow rate. And so what you end up with is you end up with a lot of data for the states that you are commonly running at. But when you're trying to then build a model that represents how the plant runs, it can be very skewed just towards the common states, and the less common states don't get very well represented. And so this is a problem that we face with a lot of industrial data sets, and there's a need to sort of rebalance the data before we go into machine learning or creating artificial neural networks and on our way to sort of digital twin type stuff. So the student developed a method, he's called it Covert. And let me just give you a brief illustration of the data set he used and some of his key results. So we were looking at a binary cycle, which is essentially what's that one? A flash and maybe it's, no, sorry, organic Rankine cycle is is the common name, is what you'd probably know it by. And then for his analysis, there was a data set with 13 different variables, 9 being input and 4 being output. So, and of course, there's uncertainties that's associated with a lot of this data as well. So you have to consider that and prevent from overfitting the data as well. So his algorithm essentially tried to look around the data set and find areas in the data set where it was relatively rare. So this is just one example of choosing an anchor point and then trying to predict using a complex algorithm around interpolation between the data set and more common areas. And so you can sort of see there, we won't go through all the details of the algorithm, but it was just, it was a method to try and predict what was going to be in between the two data sets. And one of the key things here was he was trying to make sure that you didn't necessarily maintain the same sort of distribution of data across the data set, that fundamentally you're trying to rebalance and redistribute the data and the weighting, and so that you could you would prevent yourself from sort of just producing a poor fit. And I'll show you what that means in a minute. So this is essentially the algorithm in showing sort of multiple anchor points, filling in data from a 2D perspective of just steam flow versus air temperature that has been normalized. And you can sort of see that the full name there is classless oversampling technique. So if we now sort of translate that into more of a three-dimensional representation, with power being one of the key outputs from the power station, you can sort of see where it's starting to fill in data around the edges, particularly of the data set, with relatively few in the middle. There is a few little patches there. So if we now take that data and compare it to, say, a HYSYS model, which is trying to make the connection between power, air temperature, and steam flow, you can sort of see that it definitely sort of follows that plane, but there's obviously a lot more other variables that are going on here that don't necessarily aren't fully getting represented in the Aspen model. So the next step is now to sort of look at really what's the difference does this covert algorithm of rebalancing the data make. So we've got the Aspen model is our blue plane, and that sort of represents what we think is sort of accurate for the given conditions that are being put in. And then you've got here the red plane is what would achieve in terms of a sort of a machine learning model if you were to just take the original data set. And so what you can sort of see here is particularly around the corners, the far corner there, where it's sort of 0, 0 on the steam flow and then 1, 1 on the steam flow, you can see that the model bends down dramatically. And this is not being predicted to that large extent with the Aspen model. And after we've rebalanced the data and tried to represent more fairly more of the states that we believe are possible, you can see the new machine learning model based on the rebalanced data is significantly closer and to what Aspen would predict. But at the same time, it's using the real data set. And so there's an air of sort of more realism to that model as well. So we're sort of trying to target the best of both worlds here, where we can rebalance the data set, get a much better machine learning model that can then be used and control and retrofit and other areas of analysis. So that's sort of just one piece of work that's been going on. now I just want to flip over to a very different piece of work, just to sort of give you an illustration of the breadth of research that we do. This was a research and development project done by 3 of our honours students, Ben, Alyssa, and Lana, and they studied around trying to develop a electric milk evaporator. So as Michael sort of pointed out very early, is that we have a large dairy industry in New Zealand. Fonterra is one of our key partners for our research program. And at the moment, there's most of our evaporation is happening by a combination of electricity and thermal heat or steam. So just to give you a bit of an illustration, the New Zealand dairy industry in terms of milk production is very similar to the same as California. We produce around 19 billion litres of milk each year. And what this translates into across our country is when we're at peak production, we're producing anywhere around 200 to 250 tonnes an hour of milk powder. We turn 97% of our milk into exports, and about 75% of the milk goes into milk powders for export around the world, into Asia Pacific, over into Europe as well. So the 2 key processes to produce milk powder is an evaporator and a spray dryer. We've done a lot of work with spray dryers in the past as well, and have some ongoing projects around high temperature heat pumps and spray dryers, and we've also been involved with exhaust heat recovery in the past as well. So this particular project sort of looked in at the evaporation process and asked the question of, if we were to design it as a fully electric system based on renewable electricity, which we are generally well blessed with in New Zealand, what amount of electricity would we actually need to use? And so we sort of set very early on that if we were running a 30 tonne an hour milk dryer, what would be the evaporation sort of capacity that we would need? And therefore, if we turned that sort of thermal and electrical combination that's currently there into just an electricity equivalent, we came to that we needed sort of around 5.3 megawatts of electricity for this particular plant. And the goal was, if we were to go directly to electricity and we were to achieve this number, we would be able to achieve a 44% reduction in our emissions. So we took a base case. This was based on one of our plants in New Zealand. That's one of the larger plants. Has a dryer around 30 tonnes an hour. And basically what you've got here is you've got 2 distinct processes that happen. Is first, you've got your milk, it's coming in really cold, heating it up to around 95 degrees. And that process around the 95 degrees is, we call it a heat treatment process. It's a sort of a pasteurization, but it's not necessarily a full pasteurization all the time. In this plant, it was going into a 2-effect evaporator. First effect was integrated with mechanical vapor recompression. If you're not familiar with that technology, it's basically you take the vapor that you've evaporated from the milk as you're concentrating it, recompressing it, say 5 or 6 degrees in terms of saturation temperature, and putting it back into the shell side so you can evaporate more water from the milk. And then the second effect was integrated with what we call thermal vapor recompression, or steam ejectors, where we just had steam coming in, helping to recompress a little bit of the vapor that was coming out, and the remainder was going to a condenser. And so this was the general structure of where we sort of are generally at in New Zealand. And so you can sort of see there, it was the production rate and what the milk solids percentage is coming in. That's for whole milk powder. So the team sort of started to look at developing a model of what is happening in this current evaporator. So they developed a detailed Aspen model around that, talked to a number of the experts at our OEM that's just located up the road from our university, and started to apply a technique called pinch analysis to identify how we should best integrate heat pumps, vapor recompression into the system, and then followed an iterative process of gradually putting in more and more electrical operations, so compression and heat pumps. So just to give you a little bit of a snapshot of their Aspen model, this was of the original plant. I know, yeah, and before we sort of made some modifications. So in case you're not overly familiar with the idea of pinch analysis, in essence, what we try to do is we take all of our heat sources in our plant that we have available to recover heat from. We composite them together into a common curve, and so that represents our red curve on the TH diagram. And then we take all of our blue, which is all our sinks that we need heat around our plant, and composite that into our blue curve. And from using this diagram, we can move them together, we can pinch them in order to find what is our heat recovery possibilities and our minimum and our minimum hot and cold utility that we need. So generally speaking, with pinch, you find a temperature which essentially divides the problem into two spaces, where above the pinch you need heating, generally that's steam, and below the pinch you need cooling. So this sort of analysis has been applied a lot to the chemical industries, to the refinery industries, but the key reason why we wanted to use it here in this project was to help us identify locations and ways we could take heat that was from below the pinch, upgrade it using heat pump sort of technology to be above the pinch. So let me sort of show you and walk you through some of the iterations that the team took. So first of all, if you just take all the data out of this flow sheet and you plot it with all the evaporation and condensing that you need, you get a grand composite curve, which is sort of the net heating and cooling demands across all the temperature levels that's sort of shown here. And so the first and perhaps very obvious result that they found was, of course, on effect 1, which is doing the majority of the evaporation, we should be using a mechanical vapor recompression unit, so a compressor to recompress the fluid. As we now take that out of the analysis and assume that it is integrated and part of the process, and it's no longer sort of something that we want to change, we now get a new sort of curve where we can again look and say, okay, here's another case where we're going to take, this is now essentially the effect 2. We're going to take the fluid from down the bottom here, recompress it to up the top. So that's another key result. And now if we go one step further, we now remove that from our analysis. What we find is we end up with a curve that looks more like this. And conventionally, what you would say with pinch analysis is you would sort of go, well, there's not too much more opportunity for heat pumps. A lot of this large pocket area, which is sort of all below this vapor bleed from the first effect that's possible, we should just internally heat integrate that. And, you know, there's only a little bit left here and there's not much opportunity for heat pumps. But because we were trying to go for a solution which was fully electric, the team investigated what happened if we just recompressed around the top part and then recompressed and used heat pumps around the bottom part. And so they put that into a sort of a system design using what we call the grid diagram, which is basically a really simple representation of all the sources and sinks around our plant. First putting in where we're going to place our heat pumps, and then deciding on the key matches in order to get the integration that we're looking for. So that's sort of they're skipping over a few steps, but essentially getting to this design at the end here. Let me just walk you through it very briefly. We've got our raw milk comes in. It's being preheated using condensated whey. So this is condensate that's coming from our effects and some of these other pre-train part of the preheat system. So that's sort of taking it from 8 degrees up to 68 degrees or so. We've also got integrated in here a sort of CO2 heat pump because we don't have quite enough heat to do this duty from 8 to 68. We've run out of duty, run out of waste heat from our system. So we've got about a little bit of duty coming in here from the air source heat pump. Then moving up, we've got a vapor bleed that's coming from our first effect. And the vapor bleed is just doing a little bit more preheating, just a few degrees, but even that few degrees is around about 400, 500 kilowatts. So it's not necessarily a small duty either. Then we come up to our direct contact heaters. So we've got, and it's very common when you're trying to process milk, particularly around the pasteurization type of temperatures, you need to heat it and cool it rapidly. And so what these vessels are able to do is on one side of the vessel, you've got flashing of the hot milk that's coming down. And then you've got that flashing being condensed into our cold milk that's heating up. And so this is sort of generally what happens is you can have a direct contact heater. This vessel might be running at around, or be running at 78 degrees Celsius and the pressure that's associated with that. And then we've got our second DCH, which is running around 85 degrees Celsius. And what essentially they found is by putting them two in series here, where we are able to flash and then condense in a very rapid manner, it was a better solution than trying to use a heat exchanger that you would have to more regularly clean and has the potential for sort of some bug growth, and it's just generally not desirable. So then to top off and get up to the 95 degrees, what they found is they could use a train of recompression where we take vapor bleed from their first effect, recompress it up to 90 or around 98 to 100 degrees Celsius in order to have some driving force for the the vapor to go into the milk and condense. So then we come into our first effect. The first effect is on the tube side running around 69 degrees. We've got our MVR that's now taking the vapor that's evaporated, recompressing it up about 4 degrees above boiling point. It's condensing in the first effect and then coming out. And then we've got concentrate coming out at maybe 45% going into effect 2. And a similar process, except for this time we're looking at a much higher, slightly higher temperature on the shell side. And that's just simply because we want to have a little bit more driving force. We get a little bit more boiling point rise in the second effect. And it just means we can control that final concentration well before it goes into the dryer. And then the last stage, of course, is just another heat pump in order to raise it to the temperature we need for drying. So just to sort of, I guess that's sort of our work on redesigning the milk evaporators. We're involved with a lot of different projects with our dairy industry, and that's just sort of one example. So just to sort of conclude our presentation, and before we sort of take a few questions, our team is really on a mission to help decarbonize New Zealand's process industries and embed low carbon into the design, the operation, the retrofit, and the control of units and systems. We're sort of the opinion that digital twin technology has a lot of promise, but perhaps has been a little bit overhyped in recent years. And we also believe that it needs to go much more beyond just control in the process industries. So using it for retrofit is a really big one. Making sure that we've got the right assets on the ground that don't necessarily cause us to be bottlenecked for energy efficiency and decarbonisation. So with this is we also sort of know that we need a range of tools, that it's not just one tool that is going to one approach that's going to necessarily be able to fully decarbonize our industries, and these tools can certainly leverage a lot of the digital disruption that's happening with things like IoT devices, digital twins, and that sort of thing. And then last, of course, is we're a team that is open. We love to collaborate. We're here to try and benefit our industries and just benefit globally the effort to move forward with decarbonisation and those sort of things. So that sort of concludes our presentation. Really grateful that you could come along and listen. We are on the other side of the world. Hopefully it was something of interest to you, as opposed to just another class to attend. So yeah, welcome any questions from John or whoever.
Let's thank him. I think it's really fascinating what you've been able to do, Michael and Tim, with tackling this very challenging area. And I like how you scoped it out first, like how can we have the biggest impact, and that is in processing. So it's certainly different than the US, where you have different sectors that use a lot of CO2. But I love the approach and so we're going to open it up now for a few questions. We have some time, about 4 or 5 minutes for some questions, maybe 3 or 4 questions.
I had a question. You're doing that, you had that problem where you had the uncertainty in your points of the machine learning model. Basically, and you were trying to sample more from the edges of the distribution. That's something I've run into a lot with power grid modeling as well. Do you know what the different advantages and disadvantages between the machine learning approach and like importance sampling, or like skewing your distribution to sample more from the, like statistically sample from the edges of the distribution? Does that make sense?
Well, it's probably best if I got you in contact with the with the student. He's on a different plane to me with regards to this work. Yeah, I wouldn't know the advantages and disadvantages, to be honest.
Yeah, it's really interesting to see that applied in other fields. So
yeah, no, and that's it'd be interesting to see how his algorithm would work on a slightly different data set, to see whether it would make any improvements.
If I can just jump in here, for you students that are doing postgraduate studies, one of the things that we're keen to do in our research group is to have student exchange, to where some of our PhD students come up and visit you and do some joint work, and potentially one of you guys come down to us. We see our effort as a collaborative global effort, and so if you're interested in this area a bit more, we can connect you with the Auckland student, and if you have an interest in connecting to us in a real way and coming and doing some research in New Zealand, then that is a possibility.
Daniel, it looks like you just got a plane ticket. Okay, well, thank you. We have time for about 2 more questions. So, Tim, I just had a question about some of the additional, heat pumps and other things that you're putting in. It seems like it's more heat exchangers. You kind of touched on that a little bit with this, evaporator, condenser. It kind of eases the process. You don't have to clean the heat exchangers as much. Can you say something about that? With the added complexity of this heat integration, What's been the feedback from the people who are doing this on the ground that would run this equipment? Did they say, hey, that's a great idea, but it's not practical because we have to clean these heat exchangers so often, or what kind of feedback have you gotten?
Yeah, so so typically, to give you a little bit of an idea, milk evaporators run on a cycle of about 16 to 18 hours. And all the plants in New Zealand have heat exchangers through the preheat train and all over the place in the process. And some of those heat exchangers, especially around the 45 to 60 degrees range, that's Celsius, that's where we have what we call thermophile growth. We have these sort of, and so those heat exchangers, we just have them in parallel, and we will pull some offline for maybe a couple of hours, clean them, and then the other train will come online. And so it's quite common to have parallel trains within a single, I guess, evaporation process. And then you might have sort of 4 evaporation processes in parallel as well, with 3 on, 1 off sort of arrangement. So it's not uncommon to have that sort of level of heat integration. I guess probably the biggest challenge with this particular design is it really needs to be for a new plant. It struggled to be retrofitted into an existing plant. Just space would be an issue, and generally the cost of retrofitting compared to the amount of energy savings you would get and the cost savings. So we presented this work for the first time, I think, to our dairy industry partners about a week and a half ago. So it's fairly fresh work. They were quite excited by the work, and they're quite keen to sort of figure out how we can take some of the concepts in this design and apply it in retrofit, in a retrofit manner, but not necessarily the entire electrification. So there's a few key features here that are quite different from existing designs. For example, up the top end here, where we're heating the milk in a double direct contact heating manner. That's not a design that we have in New Zealand, but it's certainly something that could save a lot of steam as a standalone sort of retrofit idea. Yeah.
It's certainly admirable with how you've been able to reduce the operating cost. So that's fantastic. Okay, we've got time for maybe one more question. And you've kind of got so any more? I've got about 10 questions, but I don't know how the okay, just one more question. What about load following, where you have like renewables with this type of process? What would you do to change the design if you said, hey, we're just going to be going off of wind or solar, and those are going to be available at different times during the day, maybe fluctuating fairly rapidly? How would you change the design if you knew you had to follow the supply instead of the kind of the opposite way, where there's load following, where producers
Yeah, well, for milk processing, it's quite hard to be a load following completely, because the product's so temperature sensitive and time sensitive. So you've got to be very careful about how long you hold the milk at a certain temperature for, and what sort of that does to the proteins. So there's certainly parts of this that you could create more load following type arrangements. So obviously all these CO2 heat pump, ammonia heat pump, both of those could simply be load following, where we're producing hot water in a storage vessel and then using that in the process. So that's one approach you could have, as creating this more of a demand response case. But I think in general, it's a little bit tricky for milk processing in particular. So yeah, I guess that's sort of my general feel. Did you want to add anything?
Yeah, just to jump in, the whole energy storage question sort of comes into play there. So Tim's hinted at the fact that, there are demands for cleaning. So cleaning in place a lot of that high temperature water can be sort of made ahead of time and then be used when it's needed. But so it would require more storage on site. So that's another area we are looking at, is how the energy storage plays out, whether it's electrical or thermal storage.
I think the one other thing I'd add to that is our grid in New Zealand is a little bit different perhaps to some other places. About 60% of our electricity comes from hydro, about 16% comes from geothermal, and both those two sources are quite, hydro you can sort of manipulate. Geothermal is very much a fairly constant rate of production, and not much manipulation can happen at the moment. And then we've sort of got some gas around. We've still got a coal-fired power station that's operating, and we've got wind is the other major electricity source. So at the moment, there's not actually a massive price differential in New Zealand between the off-peak and on-peak sort of power. But that's not to say that in 10 years' time, when we have much less thermal generation, that we start to see much bigger differences. So generally speaking, the sort of load following concepts in New Zealand are not as, I guess, they're not as of great interest at the moment, just simply because of the context of our current electricity grid. But certainly it's something that will likely to change.
Wow, well, that's fascinating. Well, let's give him a round of applause one more time. We really enjoyed the talk, and look forward to some additional collaborations. I'll follow up with both of you later. It sounds like we have some students who are also interested as well. If you don't mind just hanging on for a few minutes, just any students if I have individual questions for you. Yeah. Oh, yeah. I want to sleep. Oh, so you got it. Yeah. Okay. I was like, oh, okay. I was gonna say, like, wow, fancy freaking thing.
Definitely don't need it.
I'm gonna send you an email later. I guess let's sign off now, and then look forward to continuing the conversation later. So, yeah, good. And then I'm going to go back in my office, and I'll leave this session, but maybe we can just have a quick follow-up discussion if you guys are okay with that.
Yep, that'd be good.
Okay, fantastic. I'll leave this one right here, and I'll be over there in like a minute.
Well, thank you so much. That was fantastic.